All right, welcome everybody. Thank you for watching this video. This will be the beginning of the flipped classes. So for the rest of the semester, you'll watch these videos outside of class, and then on select days, you can go in our regularly scheduled time and work on homework, work on quizzes, work on whatever you want, as long as someone is there to help out. And you'll be able to ask them questions as well. So, today we're going to be talking about power series. This is kind of the last main topic of the course, in the form of Taylor series, is a special case of power series. But we'll talk about power series, then Taylor and Maclaurin series, and then the very, very, very end of class will be a little bit of parametric equations. But we're in the home stretch now. So announcements, again, make sure you're always working on homework, quizzes, everything in MyOpenMath. Tomorrow, Wednesday, will be a quiz day. You come in and I believe Dr. Sinclair will be there to proctor quizzes and answer any questions that you have about homework, about power series, any questions you have about the course. And then Thursday is an honorary Friday. So your Friday classes will meet on Thursday. Your Thursday classes will not meet. So this class in particular, don't show up because no one will be there to do any proctoring of quizzes or anything. So that's that. And again, your Friday classes meet on Thursday because of Apple Blossom. All right, so let's dive in just straight away to power series. This is kind of reminiscent of the last example that we did in the root and ratio test slides last time. So that was an example of a power series. So in general, a power series is any series of the form given here, the sum from 0 to infinity of some coefficients. This is called the nth coefficient. Nth coefficient times x to the n. Okay, so let me scooch this over. So it looks, I mean, it's just a series. Ultimately, it's just a series, but now we're letting the terms depend on a variable x. But everything that we talked about before, in particular, the root and ratio test, will hold. Now, a lot of the tests that we talked about before required positive terms, and so you might need to worry about what sign does x have. But the root and ratio tests don't require any sort of positivity of any terms. So we're going to use the root and ratio test most of the time when we're talking about convergence of these things. But ultimately, a power series is just a regular old infinite series, but where the terms depend on a variable x. Okay, and in fact, you can call this thing f of x if you want. Call this, it is a function of x. Okay, so this in particular is a power series centered at 0. And we can have power series centered somewhere else at some other number like x equals a, written in this form. We would still call this, some other function g of x equals that. This right here, the sum from 0 to infinity of some coefficients times x minus a to the n, which takes that form there, is called a power series centered at a. Okay, and again, a lot of the tests that we developed will still hold as far as talking about convergence of these things. And the most important tests that we developed were the root and ratio tests. We'll use those most of the time. Okay, so take a second, look back at this slide and compare it to these examples and decide for yourself which of these things are power series. Okay, so pause the video and decide what you think here. All right, I hope you paused it. So let's look at these. Is this one a power series? Well, can I write this in the form, the sum from 0 to infinity? And by the way, this beginning index doesn't have to be 0, just like always. This beginning index could be anything. Now, technically, if the power series starts at n equals 2, you can say C0 and C1 are both 0, right? But the beginning index doesn't really matter. What really matters is the form of what's inside the series. So can we write this thing in the form the sum n equals 0 to infinity of Cn times x to the n? Well, yeah, because we have an x to the n here. So let me put boxes around the things that match. Here's the x to the n. There's the x to the n. And here's Cn. That means Cn over here, there's an implicit 1 right here, right? So Cn looks like, oh, sorry, let me change back to just a regular old pencil. Cn looks like 1 over n factorial. Okay. And by the way, what's the center here? Well, this looks just like the first example. The center is 0. Okay, so this is a power series. Yes, this is a power series where Cn equals 1 over n factorial, and a, the center, is 0. Okay, let's look at the next one. The sum from 2 to infinity of minus 1 to the n over n times x minus 1 to the n. Again, can we write this in the form the sum n equals 0 to infinity? And again, the beginning index doesn't really matter. If it starts at 2, that's fine. It really doesn't matter. So the sum from 2 to infinity of Cn times x minus a to the n. Well, yes, we can. Because if I just match up what we have here, we've got x minus a to the n looks just like this x minus 1 to the n, right? And so this is going to tell me that a is equal to 1. And then I'll put a box around everything else. So we've got that minus 1 to the n over n. That has to be this Cn. Okay, so we've got a is 1. Cn looks like minus 1 to the n over n. And we've matched up everything we need for the definition of a power series. So the center for this one is a equals 1. And then our coefficients look like that. Minus 1 to the n over n. Okay. And lastly, the sum from 1 to infinity of sine of n times x all over n. This one is not a power series. No, there are no, it's called a power series because we should have x to powers, right? There is no x to the n's going on here. Okay, now this is a very interesting thing in its own right. This was a Fourier series is what this is called. And let's go look at these things in Desmos really quick. If I go to Desmos and look at all these things, there we go, we'll switch to Desmos. If I go into Desmos and look at all these things, then the first one looks like the sum from 0 to infinity. Desmos doesn't love infinity, so I'm just going to use an upper bound of 100. But that'll give us a pretty good idea of what's happening. Of x to the n over n factorial. There we go. And you might say, hey, that looks pretty familiar. And if you recognize this as e to the x, then you would be correct. E to the x is actually represented by this power series, and we'll prove that later in the class. Okay. So there's the first one. The second one, the sum n equals 2 to infinity. Again, I'm just going to go to 100 of minus 1 to the n over n times x minus 1 to the n. And there you go. You might say this one looks a little goofy, and you would be correct. Off the top of my head, I forget what this converges to, but we'll develop techniques for finding out what this looks like as sort of a simpler function of x. Just like this one we can write as the simpler function e to the x, we can do that with this function as well. And then let's look at that last one. Even though it's not a power series, we can still look at what's going on with it in Desmos. It's a pretty cool function. The sum n equals 1 to infinity. Again, I'm just going to go to 100 of sine of nx over n. And you get this weird thing going on here. And again, this is what's known as a Fourier series. And this is the Fourier series for pi over 2 minus x over 2, it turns out. And if you ever take a class on differential equations, you might see something like this in that class. But this has to do with, instead of approximating functions using a power series, the idea is like, well, why don't I approximate functions using trig functions? But we're not going to talk about that in this class. This is not a power series. Not a power series. Okay. We are going to talk about power series a lot. Okay. All right. So a note on definitions up here. You might have said, Dr. Matheson, we've got a 0 factorial in the denominator of that first one. Shouldn't that blow things up? And no, it doesn't. So as a reminder to everybody, n factorial is defined to be n times n minus 1 times n minus 2, and so on and so on and so on, all the way down to 2 times 1. You might notice that within this definition is n minus 1 factorial. So another way to define n factorial is sort of recursively. N factorial equals n times n minus 1 factorial. And so some people fight this definition, 0 factorial equals 1, but let me show you why it makes sense. 3 factorial is 3 times 2 times 1, which is 3 times 2 factorial, right? And so that tells me that 2 factorial I can actually define in terms of 3 factorial. If I divide both sides by 3, I get 2 factorial is 3 factorial divided by 3. I can do the same thing with 2 factorial. That's 2 times 1, but that's the same thing as 2 times 1 factorial. And so that tells me 1 factorial is the same thing as 2 factorial divided by 2. And so if I want to define the thing 0 factorial, well, notice 1 factorial is sort of keeping with what's happening here. I could say that that's 1 times 0 factorial to be consistent with what's above. And that tells me that 0 factorial, if I want to be consistent with how we've been defining things, should be 1 factorial over 1, which is 1. Okay. This is also 1. This is 2. 3 factorial is 6, and so on and so on and so on. Okay. So that, in case no one's ever shown you, that is why we define 0 factorial to be 1 instead of 0. Notice that this breaks if you try then to define -1 factorial, right? If you try to define -1 factorial in this way, then you try to divide by 0, and that does blow up. So you can't really extend this to negative numbers in a consistent way with this. But 0 factorial we can define to be 1. So for consistency, we define 0 factorial to be 1 and x to the 0 to be 1. And you might say, that's not weird. It is a little weird when x is 0, but for consistency with how these things work when we plug values in, we're going to be defining x to the 0 to be 1 even when x is equal to 0. Okay. So that's just a little note on some definitions. Okay. All right. So one of the things we're most interested in this class is if I write down some power series like these things, for what x's does the series converge? Okay. In other words, we developed a bunch of tests last week. If I use those tests on a power series, which has a variable in it, instead of a series that just has terms depending on n and no x's, what will these tests tell me about the convergence of these power series? Okay, and it happens to be the fact that there's only 3 possibilities for a power series in terms of convergence. So if I am looking at this power series, the sum from 0 to infinity of Cn times x minus a to the n, that's a power series centered at a. Then one and only one of the following three situations occurs. The power series converges only for x equals a. So it is always the case that a power series will converge at its center. If you plug in x equals a, then you'll get C0 plus a bunch of zeros, right? If I plug in x equals a, the sum from 0 to infinity of Cn times if I call f of x this power series, then if I look at f of a, that's the sum from 0 to infinity of c n times a minus a, which is 0 to the n. As a reminder, we're taking 0 to the 0 to be 1. Really, the reason we do that is because this looks like c0, that first constant term, plus the sum n equals 1 to infinity of cn times 0 to the n. All of those things are 0. And so we'll get c0. So a power series will always converge at its center to whatever c0 is. Guaranteed, because I'm adding a bunch of zeros, except for the very first constant term. Okay. So this, in the worst case, this is kind of the worst possible scenario. The power series will still converge for x equals a. Sort of the opposite end of that is the best case, is that the power series converges no matter what x is. And there are a lot of really nice functions that have this property, that the power series centered at x equals a converges no matter what x is. E to the x, the power series for e to the x is like this. The power series for sine and cosine of x is like this. And there's a bunch of others that satisfy that condition. But what happens most of the time is that we're somewhere in between the worst possible case and the best possible case. And that is the case where there's some number r, capital R, such that the power series converges for a minus r less than x less than a plus r, which looks like an interval centered around x equals a, right? So you're guaranteed that the power series converges for everything between a minus r to a plus r. All right, let's look at the proof of this. The proof of this just literally follows from, let's look at what the ratio test tells us. The ratio test will be your best friend in the world when you're trying to figure out what's happening with power series. Okay, so the ratio test tells me to look at the limit as n approaches infinity of the absolute value of the n plus first term. So I'm going to call it a n plus 1 for a second over a n, the nth term. Okay, but now the n plus first term looks like c n plus 1 times x minus a to the n plus 1, that in absolute value. And the nth term looks like cn times x minus a to the n. Okay, and we are guaranteed that the power series will converge if this is less than, strictly less than 1. So let's figure out all the x's for which this converges by setting this strictly less than 1. Right? Now, on the left, what do we get? We get the limit as n approaches infinity of, let's do some cancellation here. Cn plus 1 and Cn could look like anything. So I'm going to write that as just Cn plus 1 over Cn. I don't know what that looks like. However, x minus a to the n plus 1 divided by x minus a to the n just looks like the absolute value of x minus a. When you divide, notice, that cancels with almost everything up there, and we're left with that. We still want to set this to be less than 1. Okay? And now, notice, this doesn't depend on n. No n's. So I can pull that out of the limit because, yes, it has an x in it. And normally we're looking at the limit as x goes to something. But here, with the ratio test, it's a limit as n goes to infinity. There's no n's keeping this x minus a inside of the limit. I can pull it out of the limit. So this looks like absolute value of x minus a times the limit as n approaches infinity of absolute value of cn plus 1 over cn. And we still want this to be less than 1. If this is true, then the power series will converge for x. Right? So right now I'm thinking of x as kind of being fixed and thinking about what happens, what does the ratio test tell me for a specific x. Okay. Now this thing, now that we've done this, is just a number. This is some number, well, in a lot of cases, this is some number. So this is some number that we'll call capital K. That's between 0, right? It's got to be bigger than or equal to 0. And technically, if the CNs are kind of badly behaved, technically the limit here could also be infinite, right? This thing could also blow up. So I'm going to write kind of lazily that K, some number K, such that K is between 0 and infinity. Now, the case when, let's break this into 3 cases. K equals 0. In the case K equals 0, then the limit we're looking at looks like absolute value of x minus a times 0 is less than 1. And what x's does this happen for? All x, right? No matter what x is, on the left-hand side, I get x minus a times 0. That's 0. That's always going to be less than 1. So in this case, the power series converges for all x. It doesn't matter what x is. I'm always going to get something less than 1 from the ratio test in this case when k is 0. Okay. So this is sort of the best possible case. This is actually case number 2 in the statement of the theorem up here. That looks like this case right here. Okay. Let's look at the opposite case, sort of the bad case. K equals infinity. The limit blows up. Then we get something that looks like x minus a times something that's blowing up. I'm going to just call it k for a second, less than 1. This is only going to be true if x is a. If x is a, in this case, we only get convergence if x is a. Power series converges only for x equals a. Because again, if x isn't a, then I get something non-zero times something that's blowing up, and that will always be bigger than 1 at some point. Okay. Now let's talk about every other case. K between 0 and infinity. 0 less than k less than infinity. Then we get x minus a times k is less than 1. And in this case, I'm allowed to divide both sides by k. And so I divide both sides by k, which is a positive number. I get x minus a is less than 1 over k, which I'm going to call the number r. And what does this look like? Well, this looks like minus r is less than x minus a is less than r. And so I add a everywhere, and I get a minus r is less than x is less than a plus r. So in this case, power series converges for for x in a minus r to a plus r. Okay, and that's that third case there. That's this one right here. All right, cool. And that all just comes out from the ratio test. Okay, now we get that weird limit, and when I'm doing problems with this where I'm trying to figure out where is a series converging, a power series converging, I always just apply the ratio test instead of trying to remember these particular formulas. Instead of trying to memorize that, I just write out the ratio test every time, or the root test depending on how the series looks. All right, so one special note, as a reminder, the ratio test is inconclusive when, the limit as n approaches infinity of absolute value of a n plus 1 over a n is actually equal to 1. So when we're looking at power series, we'll use the ratio test to figure out where the power series converges. But we do need to test sort of the endpoints of these of this interval separately from using the ratio test. Okay. So in case 3, I don't know why I was going to write out 3 just then. We need to check f of a minus r and f of a plus r separately using our other test for convergence to check if those things converge. So again, this all falls out from the ratio test. And something that I should say up here is that this convergence, the convergence is absolute convergence. Convergence is absolute convergence. And why is it absolute convergence? Well, because we're using the ratio test. The ratio test tells us that a series that passes the ratio test converges absolutely. And so when we're talking about convergence here, by using the ratio test, that convergence is guaranteed to be absolute convergence for whatever x we're looking at. All right, so that previous theorem leads to the idea of the radius of convergence. So the radius of convergence of a power series that looks like this, and let me call it f of x, is the largest possible number r such that the power series converges absolutely for all x such that a minus r is less than x is less than a plus r. Okay. Now, if the power series only converges at x equals a, we say r is 0. And if the power series converges for all x, then we say r is equal to infinity. And technically, we found a formula for r, right? Technically, we found that r is equal to 1 over the limit as n approaches infinity of absolute value of cn plus 1 over cn. Now, I would not memorize this if I was you. I would just use the ratio test. I always just use the ratio test to find a radius of convergence. Okay. All right, so this has all been pretty abstract, high level. Let's do some examples to find the radius of convergence and the interval of convergence for some power series. Okay. All right. So we'll do the first one together. Then I'll encourage you to pause the video and try the next 2 on your own before watching me go through those. Okay, so the first one, and what we're always going to do is use either the root test or the ratio test. And 99% of the time, the ratio test is going to be my choice. Okay, so let's look at this. We've got we want to find the interval of the radius of convergence and the interval of convergence for this power series here. So finding the radius of convergence is just going to fall out from using the ratio test on this. So I want to look at the limit as n goes to infinity. We're using the ratio test of the n plus first term. So that's minus 1 to the n plus 1 times x to the n plus 1 plus 1, right? N plus 1 plus 1 divided by n plus 1 plus 1. There's the n plus first term, and here's the nth term, minus 1 to the n times x to the n plus 1 over n plus 1. The ratio test, the denominator is always just copy down what you see in the series. Okay. The center of this power series, by the way, that's going to be important to recognize is 0, right? It's not x minus anything. It's just x to a power. So the center of this power series is 0. All right. So let's look at this limit. We get a lot of cancellation, which will always happen with the ratio test. So when I look at this, I see -1 to the n cancels with almost all of those, and then the absolute values will get rid of that last -1 anyway. So let me rewrite this. This is the limit as n goes to infinity of the absolute value of, again, the -1, the absolute values get rid of it. So I'm just going to leave that -1 out because the absolute values have taken care of it. So now I've got x to the n plus 1 plus 1. That's x to the n plus 2 over n plus 2. I'm going to flip the denominator and write that as n plus 1 over x to the n plus 1. Okay. And now I get even more cancellation. This x to the n plus 1 cancels with all but one of these up here. So that is a 1. I don't get any cancellation with the other part. This looks like the limit as n goes to infinity of the absolute value of x times the absolute value of n plus 1 over n plus 2. And now that absolute value of x I can pull out in front of the limit. Okay. And when I take the limit as n goes to infinity of n plus 1 over n plus 2, the absolute values you can drop here because n is positive, right? I end up with 1 from that limit. This limit is just 1. So we get the absolute value of x, and the ratio test says, so we've taken the limit in the ratio test. We'll get absolute convergence when this is strictly less than 1. Okay. So this interval, absolute value of x less than 1, looks like -1 is less than x is less than 1. And so that tells me the radius. So, I mean, honestly, this tells you the radius of convergence. That is r. Okay, so for number 1, the radius of convergence is equal to r. Why? Well, because on the number line, if I look at this interval, -1 is less than x is less than 1, we got -1 here and +1 here. We're guaranteed absolute convergence for all of those x's between -1 and +1. But this is called the radius of convergence because what's the distance from the middle to the edge? Well, it's kind of like the radius of a circle. So that's why we're calling this the radius of convergence, and it is 1 here. Now, to find the interval of convergence, we're almost done. The interval of convergence will either look like -1 to 1, the open interval, or -1 to 1 closed interval, or it could be half open, half closed, something we call clopen, which is an annoying term. But what we need to figure out is, do we have a parenthesis here to indicate that the series does not converge at x equals 1 or -1? Or do we have brackets, or do we have a mix? At -1, does it converge? And at +1, does it diverge, for instance? So that's what we need to check now. We've checked all the numbers between -1 and 1, but now we need to actually check -1 and +1. So let's do that now. So I'm going to check x equals -1 by just plugging x equals -1 directly into the power series. Okay, so when I plug in x equals -1 directly into the power series, I get -1 to the n plus 1 to the n from that first part. And then I'm plugging in x equals -1, so then I get -1 to the n plus 1 divided by n plus 1. And when I simplify this is the sum from 0 to infinity of, so I've got -1 to the 2n plus 1. So that's an odd power of -1, which is just -1, right? So this looks like -1, the sum n equals 0 to infinity of just -1 over n plus 1. And this diverges because this is just the negative harmonic series. It is not alternating. It is just like -1, -1/2, -1/3, -1/4, -1/5, which is the negative version of the harmonic series. So that diverges. So that tells me at x equals -1, let me get rid of these right here. I want to include a parenthesis, whatever it's called. Okay. Now we do the same thing at x equals +1, and then we're done. Check x equals +1. There, I'm looking at the sum n equals 0 to infinity of -1 to the n times 1 to the n plus 1 over n plus 1. This is the sum from 0 to infinity of, well, just -1 to the n over n plus 1. And this converges by the alternating series test. So writing down the interval of convergence, I'm going to include x equals +1. And there we go. There's my interval of convergence and my radius of convergence, which you can either denote with r or ROC. I usually just use r, frankly, is 1. Okay, there you go. There's the full answer for number 1, including checking the endpoints. So checking the endpoints is a really important step for getting the actual interval of convergence. The endpoints don't play any role in the radius of convergence, other than seeing, what is the distance from the middle to the edge. But the actual how the endpoints are included, that's what we did for the interval of convergence. Okay, so I encourage you to pause the video now and try 2 and 3. Same idea, but slightly different. And then we'll talk about the answers. Okay, so hopefully you paused and tried that. Number 2, I'm going to use the ratio test. If you use the root test, that's also fine. Actually, this is one of the few times where I would say root test is better. But everyone loves the ratio test, so I'm going to use the ratio test. Okay, so we're looking at the sum n equals 3 to infinity of 2 to the n times x minus 3 to the n. This is a power series centered at 3. Okay, that's something to keep in mind. All right, so ratio test. Again, if you use the root test, good. I'm proud of you. Here's what it looks like with the ratio test. We're looking at the limit as n goes to infinity of absolute value of 2 to the n plus 1 times x minus 3 to the n plus 1. There's the n plus first term, divided by 2 to the n times x minus 3 to the n. Lots of cancellation. Leaving me with the limit as n goes to infinity of absolute value of 2 to the first times x minus 3, which is just, there's no n's here, right? So when I take the limit, I get 2 times the absolute value of x minus 3. And again, the ratio test tells me that this series will converge when the limit that we just took is strictly less than 1. And now, the other nice thing about the ratio test and the root test is don't solve for x, solve for x minus the center. Okay, this tells me x minus 3 is less than 1/2. Divide both sides by 2. Okay, this is the radius of convergence, r. Okay, now what does this interval look like? The interval of convergence looks like, the absolute value of x minus 3 is less than 2 means the interval of convergence looks like 3 minus 1/2 to 3 plus 1/2, which looks like 3 minus 1/2, 6 minus 1 is, so 5 halves to 7 halves. And actually, when I go to plug in, I usually just leave it as 3 minus 1/2 and 3 plus 1/2, and we'll see why here in a second. Okay, so now we need to check the endpoints. Okay, we're almost done. The interval of convergence looks like this, and I just need to figure out brackets, parentheses, a mix of the two, The way we figure that out is plugging in the endpoints. Okay, so I plug in x equals 5 halves. Okay, I get sum n equals 3 to infinity of 2 to the n times, 3 minus 1 half minus 3. So minus 1 half to the n, which is the sum n equals 3 to infinity. Both of those things have a power of n, so I can jam them together and just get a minus 1 to the n. This diverges. The limit of the individual terms is not 0. This diverges by the divergence test. Again, the limit of the individual terms does not go to 0. Because that diverges when x is 5 over 2, I put a parenthesis there. Okay, and then we do the exact same thing with x equals 7 over 2. Sum n equals 3 to infinity of 2 to the n times, when you plug in 7 halves minus 3, you end up with 1 half to the n. That's just the sum of a bunch of 1s, which diverges, again, by the divergence test. So I also don't include that interval. There's my interval of convergence. Sorry, I don't include that endpoint. And my radius of convergence is 1 half. So if that's what you got, congratulations. If you didn't get this, that's okay. These are tough problems. It's a new problem to do, so keep trying. All right, let's do the same thing with number 3. The sum from 1 to infinity of 2x over 3 to the 2n. Okay, so add one more blank page here. Number 3, the sum n equals, I already forget, 1 to infinity of 2x over 3 to the 2n. Okay. Again, ratio test. Ratio test. We're going to look at the limit as n goes to infinity of the absolute value of the n plus first term, 2x over 3 to the 2 times n plus 1. Be really careful about that. That's going to make or break you here. When you substitute n plus 1 in for n, put it in parentheses. Okay, over 2x over 3 to the 2n. Okay. Now, this is the same thing as the limit as n goes to infinity of absolute value of 2x over 3 to the 2n plus 2 over 2x over 3 to the 2n. All of these cancel with most of these, and so this leaves me with the limit as n goes to infinity of absolute value of 2x over 3 squared, which has no n's in it. And so this is just the absolute value of 2x over 3 squared. And I can actually pull that square out of the absolute values. That's totally fine. The ratio test tells me this converges, the series converges if the limit that we just took is strictly less than 1. Okay. Take a square root on both sides. We get that this tells us that absolute value of 2x over 3 is strictly less than 1. Oh, and by the way, something you want to take note of here is what is the center. The center is 0. So I do want to solve for absolute value of x, absolute value of x minus 0, right? So now I'll multiply both sides by 3 over 2, and I get absolute value of x less than 3 over 2. That's r. And so now I just need to check what happens. By the way, our interval of convergence then looks like, so 0 minus 3 halves gives me minus 3 halves to 0 plus 3 halves. And now I just need to figure out, do I use parentheses, brackets, what's going on at the endpoints? So I'm going to plug in x equals negative 3 halves and check there. When I plug that in up here, I get the sum n equals 1 to infinity of 2 times negative 3 halves over 3 to the n, which is just like last time. Very frequently, you're going to get a lot of sums of ones or minus ones to the ends. So the 2/3 cancels with minus 3 halves, and I get minus 1 to the n, which diverges by the divergence test. So I don't include the left endpoint. The sum n equals 1 to infinity. I'm going to plug in x equals positive 3 halves. I get the sum n equals 1 to infinity of 2 times 3 halves over 3 to the n. That's the sum n equals 1 to infinity of 1 to the n, which also diverges by the divergence test. So I don't include that endpoint either. And there we go. There's the interval of convergence. There's the radius of convergence. All right. So to finish up these slides, we're going to look at how we can represent a function, one particular function, as a power series. Okay, and it's going to be our favorite power series. We're going to look at the geometric series. So as a reminder of the geometric series. The geometric series looks like a plus ar squared plus ar cubed. Nope, I'm skipping one, sorry. A plus ar squared plus ar cubed, and so on, so on, so on. Which is the sum n equals 0 to infinity of a times r to the n. We know that that converges to a over 1 minus r if absolute value of r is less than 1. But now just plug in r equals x. Substitute r equals x. And also a equals 1 for now. I get 1 plus 1 times x plus 1 times x squared plus 1 times x cubed, and so on, so on, so on, which is the sum n equals 0 to infinity of x to the n. Sort of the most basic power series you could have. All I did was I substituted a equals 1 and r equals x. So this is still, from the geometric series formula, 1 over 1 minus x. And I already know the interval of convergence and radius of convergence as well. Just I substituted r equals x, so that means absolute value of x less than 1. That's where this converges. And we know this diverges if absolute value of x is greater than or equal to 1. Okay, so the interval of convergence here for this power series is negative 1 to 1, open parentheses, and the radius of convergence is 1. Okay, so we've kind of already done a power series, but I was just using an r instead of an x, and so we know already that we can represent the function f of x equals 1 over 1 minus x, at least on the interval minus 1 to 1, by the power series, the sum n equals 0 to infinity of x to the n. Again, as long as absolute value of x is less than 1. And let's go verify this in Desmos really quick. If I go into Desmos and look at 1 over 1 minus x, and specifically for absolute value of x less than 1, and compare it to the sum n equals 0 to infinity, which again, there's going to be a tiny bit of weirdness because Desmos hates infinity. So I'm just going to go 0 to 100 of x to the n. Then these match up except at the endpoints. So if I look at absolute value of x strictly less than 1, there we go. Okay. If I could put in an infinity here, we would see perfect matchup. But there we go. See, they line up. These two things are the same function. once I replace that upper bound with an infinity. Amazing. Okay. Now, outside of the interval of convergence, these don't match up because the power series is blowing up, right? There's 1 over 1 minus x outside of the interval of convergence. Here's the power series. It still is just blowing up at x equals -1, +1. But it's still cool that we can represent this this function 1 over 1 minus x with this power series, and it will be really useful to us when we're doing things like integrating certain really difficult functions. It turns out that if you can write down the power series for a function, it's much easier to integrate that as opposed to integrating the original function. So these power series are really cool, really useful, and we're going to see more later about how we can use these to help us with things like integration and differentiation. All right, so this video has gone on long enough, so I will begin the next video with this example here, using the geometric series formula to write out what these power series are in terms of functions. Okay, I would encourage you to try this out before you look at the next video. But in short, I want to write this as a simpler function that doesn't involve a power series using this formula right here. Okay, so that's how I'll start the next video, and then we'll get into a little bit of properties of power series and finally move into Taylor series and Maclaurin series. So thank you all for your attention. Tomorrow you'll come in for quizzes and questions, and then I'll have another video posted for you shortly. Have a great rest of the day, everybody.